Imagine this. You're playing The Legend of Zelda, Tears of the Kingdom. You're fighting monsters, chasing down dragons, dying in embarrassing ways. You sit by the campfire and begin to ponder. Where's Zelda? Why is it her legend when I'm the main character? Will I ever find her? What's the acceleration due to gravity assuming that all objects are in free fall? If this last question is most interesting to you, then you're in luck. This is my final project for AP Physics 1, a physics-based analysis of The Legend of Zelda, Tears of the Kingdom. In this project, I will be studying different game mechanics and the way that different objects interact with each other. I will mostly be focusing on kinematics and dynamics, but there will be other physics principles involved when calculating values. For all of our experiments, we'll have to make some assumptions about the game, but we'll cross that bridge once we get there. To reduce experimental uncertainty, we will be using video analysis in every single experiment. Here are the exact steps I take when gathering data. You can pause the video to read them. After we finish the experiment, I'll do some real-world comparisons to see how realistic the in-game physics are, if applicable. That's pretty much everything. But before we can start doing experiments, let's introduce our test subject, Link. This is Link. Based on this Reddit post, he's 1.73 meters or 5'8". Using a balance beam that I rigged up here, we can determine that he weighs 10 apples. In this video, we will consider one apple to be 1 kilogram. If you look at the bottom right of the screen, there's a mini-map. That mini-map has a bunch of coordinates. Every time a coordinate changes by 1, Link moves 1 meter. Link can walk, speed walk, run, and sprint. Unlike literally the rest of the world, Link experiences air resistance. He can fall normally, belly down, dive to fall faster, or paraglide to fall slower. He can jump on a shield to shield surf. Link can also drink elixirs to buff his stats. Don't ask what they're made of. No matter how much heavy stuff Link has on him, his weight never changes, and regardless of how much clothing he has on, he falls at the same rate. What else can Link do? Oh yeah, he has magic powers. To further reduce experimental uncertainty, we will be using these magic powers to help set up our experiments as accurately as possible. Ultra Hand will be used to precisely move objects into place. Fuse will be used to attach materials to shields. Recall will be used to give us time to position the camera in order to get accurate data. Ascend and Auto Build will help us set up the experiments. Link can also use devices called Zonai devices. There's a lot of these things. For many of the dynamics experiments, we will be analyzing these devices. And that's Link for you. Now, with that out of the way, let's start doing experiments. Let's start things off easy. The first question we want to answer is how fast is Link when walking, speed walking, running, and sprinting? Essentially, we're looking for a speed when doing those actions. Here's our experimental constants. Link will be moving directly north on a flat grassy field, and he has consumed no hasty elixirs. To find speed, we will be taking a position time graph and then finding a slope to get velocity, the absolute value of which is speed. The units will be meters per second. Here's the procedure. Feel free to pause to read it. Let's put this procedure to action. Here's the experiment. And here's our data. I used Desmos to graph the data and then used the regression feature to find the line of best fit. Here's where an experimental constraint, the limited space available, kicks in. The faster Link is going, the more this constraint affects us. This is why sprinting only has 4 points of data instead of 5. At that point, Link has essentially run off the plot. Here's the results. And here's the results compared to the average speed of real people. I've linked all the sources in the description. There are unfortunately no studies on speed walking. Compared to real people, Link is really fast. Alright, let's spice things up a bit. Tears of the Kingdom allows you to make elixirs that change Link's stats. One such elixir is the Hasty Elixir, which increases Link's speed. Elixirs have 3 strengths: low, mid-level, and high. Our next experiment will be answering the following question. What is the correlation between Link's running speed and the strength of a Hasty Elixir? We will be finding speed in the exact same way as we did previously. Here's our experimental constants. Link will be moving directly north on a flat grassy field. He will be running in every trial. Here's the procedure. Here's the experiment. And here's our data. And finally, here's our results. It seems like running speed is proportional to elixir strength. Why don't we plot that on a graph? It is linear. Based on the data, running speed increases by 0.622 meters per second when elixir strength is increased by 1. There is one more factor that can affect a Link's running speed: the surface he's running on. The question we want to answer here is, what is the effect of different surfaces on Link's running speed? Here's our experimental constants. Link will be moving directly north on a flat surface. He will be running in every trial. He will not have consumed any hasty elixirs. Here's the procedure. Here's the experiment. Here's the data. Finally, here's our results. Based on this data, running on snow and sand are about the same speed, and are both about 1 meter per second slower than running on grass. Alright, I'm sick of walking Link around. Let's move on to horses. In The Legend of Zelda Tears of the Kingdom, horses can have 4 different star ranks for speed: 2, 3, 4, and 5. Why there's no 1 star, I don't know. Oh yeah, and ignore the spurs on the screen. That's not the indicator for speed. Anyway, we're going to be asking the following question for this experiment. What is the correlation between speed stat and the actual speed of the horse at a gallop? Here are my test subjects, beloved horses. Each one has a different speed stat. Here's our experimental constants. Link, riding his horse, will be moving directly north on a flat grassy surface. The horse is galloping in every trial. Here's the procedure. Here's the experiments. Here's the data. The experimental constraint of limited space really hurt us here with how fast the horses run. But by decreasing the time intervals that position is taken, this has helped. Still, especially with 4 and 5 stars, it's difficult. And here's the results. Based on the data, the speed of the horse spikes between 3 and 4 star rank, but below and above that it doesn't change that much. This is interesting because I've always felt like 5-star horses are much faster, but I suppose it could be the placebo effect. For comparison, the average running speed of a domestic horse is about 30 miles per hour, or 13.41 meters per second. That makes a 4-star horse about an average horse in real life. No more running around. Let's finally answer the question addressed in the intro. What is the acceleration due to gravity? In Tears of the Kingdom, there are actually 2 different g values that exist in the world. There's one g value that most of the map follows, and then there's the g value in the water temple. The water temple is surrounded in a low gravity zone, in which the acceleration due to gravity is a lot lower. But how much lower? Let's find out. In order to find this value, we will be dropping an apple next to a bunch of crates stacked on top of each other. We will be assuming that crates are exactly 2 meters tall and that objects are always in freefall. In order to find the acceleration of the object, we will be using Capstone's video analysis feature. Here's our experimental constants. The apple will be dropped from rest above the ground, and the experiment will be conducted on a flat surface with no updraft. Let's get started. Here's our procedure. Here's the experiments. Here's our data. And here's the results. Based on this information, the G value at the water temple is about 4.6 times less than outside the water temple. When playing the game, it certainly feels like this. Now, is this all realistic? The acceleration due to gravity in much of the world is 3 times as much as it is in real life. But if you've been paying attention, you might realize just how small a meter is in the game. I mean, Link is almost 2 meters tall and he's considered to be short. So it makes sense. If you decrease the scale of the meter, then you're gonna increase the acceleration. Let's take a look at the various forces found in the game. For our first experiment, let's answer this question. What is the coefficient of friction between grass and different fused materials on shields? In Tears of the Kingdom, you can fuse almost every movable object to your shield. Most objects you can't surf on, but with others you can shield surf, and different materials have different coefficients of friction. We will be looking at 2 different fused materials, plus and control with nothing fused, to determine which is the best for shield surfing purposes. The first fused material we will test is a Zonai sled fused to a shield. The description says that sleds allow us to slide with minimal friction. We'll see about that. The second fused material is frozen meat fused to a shield. It's been determined in the Zelda community that a frozen meat shield has the least friction out of all materials. Let's put that to the test. Before we can start collecting data, we need to figure out how the heck we're going to find the coefficient of friction. The easiest way to do so would be to use Newton's second law, or F net equals ma. Let's draw a free body diagram of Link to find the F net. Because the normal and gravitational forces cancel, F net is equal to the force of friction, which is equal to the normal force multiplied by the coefficient of friction. Alright, now we have mu in the equation. The normal force is going to be equal to Link's weight, which is mg. Hold on, there's m on both sides of the equation. It cancels. Using algebra, we can isolate mu, which gives us mu equals a over g. That means that all we need to find is Link's deceleration when he's shield surfing. We found g in the last experiment. In order to accurately find acceleration, we will create a position time graph and then linearize it. Afterwards, we will take the slope, which is 1/2 acceleration, and multiply it by 2. Right, now that we know what data we need to collect, let's get started. Here are the experimental constants. Link is shield surfing with the left joystick pushed forward the whole time. He is surfing directly north on a flat, grassy surface. Here's the procedure. Here's the experiment. Here's the data. Note that some of the tables don't have all the points that I collected. However, the graphs do. And here's the results. Based on this information, we can in fact confirm that the icy meat shield is the most slippery of them all. Here's a chart with a bunch of different friction coefficients for reference. The results that we found are actually pretty accurate. 0.4 is quite a low coefficient of friction and is the same as Teflon on Teflon. In addition, the frozen meat shield has a similar coefficient of kinetic friction as real ice on ice does, which is interesting. Another force we can take a look at is spring force. Here's a Zonai spring. It's capable of exerting a force on objects. Let's answer this question. What is the spring constant of a Zonai spring? To find spring constant, we will be assuming conservation of energy. Here's the energy bar chart for this situation. Based on the bar chart, the equation is 1/2 k delta x squared equals to 1/2 mv squared. Delta x is the spring compression, m is the mass of the moving object, v is the initial velocity of the object, and k is the spring constant. The object in question here will be a single apple. By measuring the spring when extended, we can find its compression. We will assume that the apple is 1 kilogram. To find spring constant, we still need to find the apple's initial velocity. We can do this using kinematics. Here's an equation we can use to find initial velocity. V final equals to V initial plus AT. We know that at the top of the apple's path, its velocity is 0, and through its entire motion, its acceleration is -30. All we need to find is time. Time in this case would start once the object starts going up and end when the object is back down to its original height. We divide by 2 to find the time at which the object's velocity was 0. Plugging that in, we can find its initial velocity. The reason why we're using time to find initial velocity is because the apple goes really high when the spring is launched. Too high for the camera to catch it, even when backed up super far. Thus, we're using time to get the most accurate values we can. In addition, to ensure better results, we are using a zonized stake to secure the spring to the ground. Now that we know what data we need to collect, we can run our experiment. Here's the procedure. Here's the experiment. Here's the data. And here's the results. Plugging everything back into the equation, we can determine that the spring constant of a zonized spring is 1,635.4 newtons per meter. Finally, let's tackle air resistance. It is known that Link experiences air resistance in the game. If you drop an item while falling, the item will keep accelerating downwards while Link falls behind. I'm even diving here and the soup ladle is still so much faster. I'm never seeing that ladle again. This is even true for objects that are larger than Link, like these carts. Here is the equation for air resistance. It is most helpful to us to find the air resistance when the object is at terminal velocity. Rho is the density of the fluid, which is air in this case. V is the velocity of the falling object. A is the horizontal cross-section of the object, or the surface that's facing the ground. And CD is the drag coefficient. But wait, we don't really need to use all this to find air resistance. At terminal velocity, where an object falls at a constant velocity, the forces are balanced. Therefore, the force of air resistance is equal to the weight. What we can solve for instead is the drag coefficient, which is similar to the friction coefficient. An object's drag coefficient is its resistance as it moves through a fluid. We will be solving for the drag coefficient when Link is at terminal velocity in 4 different positions of falling. Those are normal falling, belly down falling, diving, and paragliding. The question for this experiment is what is Link's drag coefficient when he is falling in different positions? Here's the formula for drag coefficient. First, we need to find Link's horizontal cross-section. By taking a photo of him standing on top of a crate and considering him to be a rectangular prison, we can determine that his horizontal cross-section for normal and diving is very roughly 0.33 meters squared, for belly down falling is 1.5 meters squared, and for paragliding is 2 meters squared. The force of air resistance is equal to mg, which in Link's case is 30 times 10 equals to 300 newtons. We will assume that the density of air is 1.293 kilograms per meters cubed. Finally, we need to find the terminal velocity. To do so, we will create a position time graph of Link falling, and then take the average rate of change in each time interval to find his velocity. When the velocity becomes constant, that's when we know we found our terminal velocity. Here's our experimental constants. Link will be falling in a place with no updraft. Here's the procedure. Here's the experiments. Here's our data. And here's our results. Now let's plug this information into our equation to find the drag coefficients. Here they are. Here's a chart to compare our data to real-life skydivers and model rockets. Obviously, there's some pretty major differences here. Our drag coefficient for diving is much smaller than in real life, and our drag coefficient for paragliding is much larger. The first disparity is likely a game design choice. If Link fell as fast as a person did in real life, it would make the game feel horribly slow. The second disparity is due to the fact that the paraglider is tiny compared to most parachutes, and that Link falls super slowly when he's using it. Again, game design. It allows for the player to maneuver through the air easily and prevents the screen from being blocked off. A big part of Tears of the Kingdom is the Sky Islands, which require the paraglider to maneuver. By making the drag coefficient massive here, it lets Link traverse much easier. Tears of the Kingdom is easily one of my favorite games of all time. The developers had this game in the works for years and years, testing every game mechanic, giving every NPC a story, and adding in little details that people are still finding today. The physics engine in this game is stable, accurate, and just generally incredible. Every interaction between objects is completely physics-driven. Everything has mass, momentum, inertia, you name it. That is the only reason why I was able to do so many experiments in this game. I've linked an article that covers an interview with the game developers about the physics engine. The developers go in depth about how they did their best to be faithful to the real world, but also made sure that the game experience remained fun. They kept players in mind above all else. And the result? A wheel that could drive a vehicle using a motor's torque, just as it works in real life. Water resistance. A calculated mass and momentum for every object based on volume. By creating such a strong physics engine, it allowed for a ton of creativity on the players' parts. Here's a few examples found on the subreddit r/HighRollEngineering. All of these crazy machines built by absolute mad lads can happen because the physics for this game are so secure. Truly, this game and its physics are a work of art.